In today's lecture, we are going to show that Fatou's lemma. What Fatou's lemma says that if you have a sequence of measurable function, then you take integration and limit infimum outside the integration that will be greater than or equal to integration limit infimum taking inside the integration, and this is one of the fundamental result in the Lebesgue integration. Okay, and later on we are going to prove another very important result that every measurable function or every integrable function can be approximated by a sequence of measurable simple functions, and that is also one of the important theorem because they are the they are the theorems that we are going to use again and again in proving many result in Lebesgue integration. Okay, so now let us go to Fatou's lemma and monotone convergence theorem. Alright, so what Fatou's lemma says that let Fn be a sequence of non-negative measurable functions. Okay, so then limit infimum integration Fn dx will be greater than or equal to limit infimum integration limit infimum Fn dx. Alright, so this is Fatou's lemma statement. So this sequence is a sequence of non-negative measurable function, and then this inequality holds true. Alright, so let us see. Let us put f is equal to limit infimum Fn. So the function limit infimum Fn, it is represented by f, and then f is non-negative measurable function. Okay, since the sequence is a sequence of non-negative measurable function, the limit f is also non-negative measurable function that we have already shown. So from the definition we have what we define, how we define integration of a non-negative function. Integration of a non-negative function is equal to supremum integration phi dx, where the supremum is taken over all measurable simple function phi such that phi is less than or equal to f. That is the definition of integration of non-negative measurable function. So if we are able to show that integration phi dx is less than or equal to limit infimum integration Fn dx for all measurable simple function phi. So if we are able to prove this inequality for all simple measurable function phi such that phi is less than or equal to f, then even if you take supremum here, that will be less than this side. Okay, so that is supremum integration phi dx less than or equal to limit infimum Fn dx. But according to the definition of integration, this is nothing but it is the integration of f dx. But integration of f dx is f means limit infimum Fn. Alright, that way we will be able to prove Fatou's lemma. So okay, so it is sufficient to show that integration phi dx is less than or equal to limit infimum integration Fn dx for all measurable simple function phi such that phi is less than or equal to f. So if we are able to prove this result for all simple measurable function phi less than or equal to f, then our goal is achieved. Okay, so case number 1, suppose the integration of phi is equal to infinity, that is summation I running from 1 to n ai, measure ai is exactly equal to infinity. Okay, because integration according to the definition is equal to this summation, and this is infinity means this sum is equal to infinity. Alright, so since ai are finite, alright, for some I, since ai's are finite but this sum is equal to infinity, one of the measure of the set ai, capital AI, should be infinity. Okay, so measure ai is equal to infinity and phi is greater than a, means when measure ai is equal to infinity, phi cannot be 0. So phi is greater than some positive number a, that is phi x is greater than when x is a member of capital AI. So then we write gkx is equal to infimum j greater than to k fjx. Alright, so gk, they are increasing function, and we define capital Bn, that is exactly equal to x such that gkx is greater than a for all k greater than to equal to n. So then Bn, they are measurable function set. So it is obvious that Bn is a subset of Bn plus 1, that is Bn is an increasing sequence of measurable set, and for each x, gkx is monotone increasing, because by the definition of gk it is monotone increasing. Alright, so therefore k tends to infinity, since gkx is a monotone increasing, it has limit. So k tends to infinity, gkx is equal to supremum j greater than or equal to k fjx. Alright, but that is exactly equal to limit infimum fn x, that is we put f of x, but f of x always greater than or equal to phi x, but phi x is still greater than a. So it follows that x belongs to ai, implies that x belongs to Bn for some n. I am going to explain this one in another window now. So if you understand this one, the result is easier. So we have ai is a subset of union n going from 1 to infinity Bn, that is ai is a subset of limit Bn, because this Bn is a sequence of increasing function, their limit is exactly equal to union, n going from 1 to infinity Bn is the limit Bn. Okay, so hence if you take a measure both side, but this one measure has infinity measure, so infinity is equal to measure ai, that will be less than or equal to measure limit Bn, but that limit and measure can be interchanged, because Bn is a sequence of increasing function, it has limit, so limit Bn, but measure Bn exactly equal to that one, limit measure Bn is exactly equal to infinity, because this is going to be greater than infinity, so the only possibility is this itself is exactly equal to infinity. Okay, so that is what we get. Alright, so now let us illustrate the fact that x belongs to Bn for some n. Okay, so limit k tends to infinity, gkx is exactly equal to f of x, that we have shown, but f of x is greater than or equal to phi x still greater than a. So then if you put epsilon is equal to f of x minus a, since limit tends to k tends to infinity, gkx is f of x for a given epsilon, if you choose epsilon deliberately this much, we should be able to find a positive integer n such that modulus f of x gkx is that is exactly equal to, because f of x is greater than gkx for every k, because gk they are monotone increasing, so f of x will be greater than any gk, that you can write after dropping the modulus f of x minus gkx, that is less than epsilon for all k greater than or equal to n. So it follows that f of x minus gkx is less than f of x minus a for all k greater than or equal to n. So after cancellation, what you get? gkx is greater than a for all k greater than or equal to n. So if this condition fulfilled for all k greater than or equal to n, then this x is a member of Bn, that is the definition of Bn. So x belongs to Bn whenever x is a member of capital Ai, that is what we conclude. But for each n we have for each n we have fn is greater than or equal to gn, therefore integration fn dx will be greater than or equal to integration gn dx, and that will be strictly greater than a times chi Bn, because gn will be greater than a on Bn. So therefore this inequality holds true, but this one is exactly equal to measure Bn times a. Alright, so limit infimum integration fn dx is equal to infinity, because as n tends to infinity this side is infinity, so that the integration as n tends to infinity this part will be greater than infinity, means this itself is equal to infinity. Alright, so this one is infinity and this one is infinity, so equality is there. So therefore this is true when the Fatou's lemma is true when integration of phi x dx is equal to infinity. Alright, so now let us show second case, the case that integration of phi dx is finite. Then we write c is equal to x such that phi x is strictly greater than 0. Alright, so since integration of phi dx is finite, we have measure of capital C is finite. Okay, so let m be the largest value taken by phi. M is the largest value taken by phi. Then we can write Cn is equal to x such that gkx is greater than 1 minus epsilon times phi x dx. K greater than equal to n. So since epsilon, you take less than 1 but positive, so 1 minus epsilon phi x will be less than phi x. All right, will be less than phi x. Phi x will be greater than, and this will be a number that will be less than phi x. So if this is a, then phi x is greater than a. So in the previous step, you can apply. So the reasoning of previous step can be applied here also. So then you define gkx is equal to infimum j greater than equal to k fjx, and cn are measurable set, because gk are measurable functions, so cn are measurable set. So cn, they are subset of cn plus 1, and that as we did in bn are subset of bn plus 1 earlier, that can be used here also, the same logic. And here also C is a subset of union n going from 1 to infinity cn, the same thing as we did in ai is a subset of union an. Like that, you can easily deduce that C is a subset of union n going from 1 to infinity cn. So cn are increasing sequence, therefore C difference cn, they are decreasing sequence of set. Okay. So therefore, for decreasing sequence of set, you take intersection and going from 1 to infinity, that is exactly equal to intersection 1 and going from 1 to infinity C intersection cn complement. All right. So, but C intersection n going from 1 to infinity cn complement is exactly equal to, by De Morgan's law, this one. But since C is a subset of union n going from 1 to infinity cn, so complement of union n going from 1 to infinity cn will be a subset of complement of C. That is what I am writing here, C intersection C complement, that is phi. So what does it say? This intersection is equal to phi, but this intersection is equal to limit. So this intersection is nothing but limit n tends to infinity C minus Cn. So limit C minus Cn is exactly equal to phi. So m limit C minus Cn is exactly equal to limit m C minus Cn. So you can interchange limits and measure, and that is equal to 0. So there exists capital N such that measure C minus Cn is less than epsilon for all n greater than equal to capital N. All right. So then Gn is greater than equal to Gn chi Cn, and Gn chi Cn is greater than equal to 1 minus epsilon phi chi Cn. So then if you put integration all the side, you get this inequality. All right. And that is exactly equal to 1 minus epsilon integration Cn phi x dx. Okay. That is, you can take out 1 minus epsilon, then integration phi dx. But this one you can write as a disjoint union of C and C minus Cn. So ultimately you can write in this form integration phi dx minus integration C minus Cn phi dx. Alright. So but here this 1 minus epsilon is small number multiplying in this factor. So if you multiply only this factor, so that will be greater than this one. Alright. So 1 minus epsilon integration phi dx minus 1 integration C minus Cn phi dx. So here you are dropping the small multiplication factor 1 minus epsilon. Therefore, so subtraction of bigger number will be less than this one. Alright. That is exactly equal to integration phi dx minus epsilon integration phi dx minus integration C minus Cn phi dx. Okay. So that is greater than equal to this one. Because why I am writing greater than equal to, because this number this is less than this one. All right, this one is less than this one, so you are subtracting a bigger number here, therefore this will be less than this side. Okay, since epsilon is arbitrary, what do we have? Integration Gn dx is always greater than equal to integration phi dx. All right, so again Fn is greater than equal to Gn, therefore integration Fn dx will be greater than equal to integration Gn dx, and that is greater than equal to integration phi dx. So it follows that integration phi dx is less than equal to integration Fn dx for all measurable simple function phi, such that phi is less than equal to f. So therefore taking supremum here also will be less than that side. Alright, therefore integration phi dx is less than equal to limit infimum integration Fn dx. Okay, so taking limit infimum here also, this inequality doesn't change. Okay, So hence the result follows. The Fatou's lemma now we have proved. So next we are going to prove another very important result called monotone convergence theorem, and that is we are going to use the Fatou's lemma. Okay, so this theorem is very short because we are going to use Fatou's lemma. So what the statement of the theorem says that let fn be a sequence of non-negative measurable functions such that fn dx is monotone increasing. So fn dx is monotone increasing means f1 will be less than or equal to f2x, f2x will be less than or equal to f3x, like that for each x. Let f is equal to limit fn, let us put f is equal to limit fn, then integration f dx is exactly equal to limit integration fn dx. That means the limit this limit can go inside the integration, and that is all about this theorem, monotone convergence theorem. Okay, let us prove it from the Fatou's lemma we have. So since the statement of the theorem is exactly satisfies the statement of the Fatou's lemma, we can apply Fatou's lemma here. So Fatou's lemma, so limit infimum, if you take inside the integration, that will be less than or equal to limit infimum taking outside the integration. So if you put f is equal to limit infimum, and that is exactly equal to limit fn, then that is f. Alright, so that will be equality number 1. It is given that fn dx is monotone increasing for each x, and therefore the limit f will be always greater or equal to fn for all n. So therefore integration of f dx will be greater or equal to integration fn dx for all n. So and then if you take this side limit supremum also, the inequality doesn't change. Okay, so limit supremum, but limit supremum is always greater than or equal to limit infimum. So we have this inequality, that is integration f dx will be greater or equal to limit infimum fn dx. This is inequality number 2. So combining 1 and 2 we get the result. Alright, so limit supremum integration fn dx is equal to limit infimum integration fn dx, that is exactly equal to limit integration fn dx. Okay, the equal value of limit supremum, limit infimum, we call it just limit. Alright, so this one we have. Now the important theorem, another one, the theorem on approximation of non-negative measurable function by simple measurable function, because for simple measurable function we know how to find out Lebesgue integration. So if a given non-negative measurable function can be approximated by simple measurable function, then we will be able to find the integration of this non-negative measurable function also. Alright, so that is the method. Let us see. Theorem, let f be a non-negative measurable function, then there exists a sequence phi n of measurable simple functions such that for each x, phi n x is monotonic increasing and converging to the phi f of x. Alright, so that is the statement of the theorem. Okay, every non-negative function can be approximated by a sequence of simple measurable function. So that way we can say, we can understand also. Now see, let us prove for each natural number n. So define enk is equal to what is enk? Enk is the collection of set x such that f of x is less than or equal to k divided by 2 to the power n, but f of x is still greater than k minus 1 divided by 2 to the power n. So for x in enk, f of x will be less than this one but greater than this one. Okay, what about k? K is running from 1 to n times 2 to the power n. K is running from 1 to n times 2 to the power n, and then we define fn. What is fn? Fn is exactly equal to those x such that f of x is still greater than n, that we call it fn, and these are enk. So we are going to illustrate this enk when n is equal to 2. When n is equal to 2, then k can run from 1 to 8, because 2 into 2 to the power 2 is 8. Alright, so let us see construction of phi n. Next, let us construct phi n. You can put phi n is equal to summation k running from 1 to n times 2 to the power n k minus 1 divided by 2 to the power n chi en k plus n chi fn for its natural number n. Alright, so the function phi n are simple measurable functions. These are simple measurable functions. From the construction it is obvious, and it is seen that they are increasing also. You can easily check it. Okay, so you can easily check it. Phi n plus 1 will be greater than or equal to phi n. So if you have some doubt, you can give me message in the comment section, and we can discuss for its natural number n. Alright, so now let us see how does it look like ank and fn when n is equal to 2. So I told you when n is equal to 2, k run from 1 to 8 because n into 2 to the power n is equal to 8 when n is equal to 2. So enk and fnk, let us see some simple illustration, graphical, so you can easily refer to this one when you are confused. Let us see. So this is the graph of the function f of x, so then 1 upon 2 to the power 2 is 1 by 4, it is here, 1 by 2 is here, 3 by 4 is here, 1 is here, 5 by 4 here, 6 by 4 is here, and 7 by 4 will be here somewhere here, but I am dropping that because of the space, less space, and 2 is here. Alright, so let us see. And then since the graph doesn't touch this line, what is this line? This line is 1 upon 4. Horizontal line, this blue line is 1 upon 4. Since the graph doesn't touch here, so what is e21? E21 is equal to 5 because there is no point f of x is exactly equal to 1 by 4. Okay, alright, so therefore e21 is 4. How about e22? So e22, according to the definition, e22 is exactly equal to those point x such that f of x is less than or equal to 2 by 4 means half, and that is still greater than 1 by 4. So this is 1 by 4, the graph should be 1 by 4, it is okay. The graph should be less than 1 by 2 than this portion. Alright, this portion. So it is going up to infinity, therefore e22 will be any point here in e22, the f of x will be between 1 by 2 and 1 by 4. Okay, this is 1 by 4, this is 1 by 2. So e22 will be this much set, all the set starting from here up to infinity will be e22 according to this function. Alright, let us see how about e23. E23 according to the definition such that it should be x such that f of x is less than or equal to 3 by 4 but should be greater than 1 by 2. Okay, so 1 by 2 line is this one, it is above, this graph is above in this section 1 by 2, but it is below 3 by 4. Therefore e23 is this much set, that is point here. For the point here, f of x will be between 3 by 4 and 2 by 4. So like that, e24 is this much. Okay, and then e25 is this set like that. Okay, e26 and e27 will be like that. How about the f2 by the definition x such that f of x is still greater than 2. So this horizontal line is 2. Okay, y is equal to 2. So the graph is above this horizontal line for the point f2 here. So f2 will be this much set, starting from here up to infinity will be f2. Okay, so then how about the phi 2? Phi 2 into 1 is 0. Okay, phi 2 into 1 is equal to 0. When n is equal to 2, we have the simple function phi 2, and then phi 2 is equal to 1 upon 4 when x is in e22. Okay, when x is in e22, phi 2 is equal to 1 upon 4. Similarly, when x in e23, phi is equal to 1 by 2, and when x is in e24, phi is equal to 1, like that. Okay, so in e26, phi 2 is equal to 5 4, in e27, like that we have. Okay, how about f2? When x is in f2, phi 2 is equal to exactly equal to 2. Alright, so phi 2 is exactly equal to 2 when x in f2. Okay, so that is the explanation or illustration of e2k, enk, phi n and fn. Okay, for the case when n is equal to 2 and for that specific function f, I have drawn the graph. Okay, so let us show the convergence of phi n x. We have constructed phi n x like that. Now we are going to show that phi n x is converging to the function f of x. Okay, so if x is a member of fn plus 1, then f of x is greater than n plus 1 from the definition, and that is greater than n, so x belongs to fn. Therefore fn, they are decreasing sequence. F1 will be superset of f2, f2 will be superset of f3, like that. Okay, so therefore by De Morgan's law, f1 complement will be subset f2 complement, like this. Okay, if fx is finite, then x belongs to fnc. Okay, if fx is finite, x belongs to fnc for all n greater than or equal to capital N. After some step, x should be member of fnc and the complement of fn. And in that situation, you can easily verify this one, f of x minus phi n x modulus is strictly less than 1 by 2 to the power n for all n greater than or equal to capital N. Okay, so if f of x is infinity, then f of x will be greater than any natural number n for all n greater than or equal to 1. Alright, so it follows that x belongs to fn for all n greater than or equal to 1. That means x is in the intersection n going from 1 to infinity fn. Okay, so phi n x is exactly equal to n for all n greater than or equal to 1. That is, limit n tends to infinity, phi n x is exactly equal to infinity, that is exactly f of x. Okay, so in both the situation, limit n tends to infinity, phi n x is equal to f of x. So now we are able to prove that a given non-empty measurable function can be approximated by a sequence of simple measurable functions. Okay, so corollary, by monotone convergence theorem, what we have? By monotone convergence theorem, we have integration f dx is exactly equal to limit phi n dx. So ultimately what we have shown is that, the integration of a simple non-negative simple measure the integration of a non-negative measurable function can be found out by using this formula, limit integration phi n dx. Alright, where phi n is what? Phi n is the sequence of simple measurable function which is converging to the function. Okay, so theorem on integral of the sum of non-negative measurable function. Okay, let us see, this is small theorem. Let f and g be non-negative measurable functions, then integration of sum of the function is exactly equal to integration of the function f plus integration of function g. Alright, proof, consider the simple function phi less than or equal to f and psi less than or equal to g, and then phi can be written in this form and psi can be written in this form. Okay, and union of ai is r, union of bj is equal to r, and then union this you can write in this form. So after simplification, you can write union ij running from 1 to nm, ai intersection bj is exactly equal to r at disjoint union. Okay, so on ai intersection bj, we have phi plus psi is equal to ai plus bj, but ai plus bj is less than or equal to f plus g. Alright, therefore phi plus psi is a simple function such that phi plus psi is less than or equal to f plus g, and phi plus psi x is exactly equal to summation ij running from 1 to nm, ai plus bj chi ai intersection bjx. Alright, it follows that integration over ai intersection bj phi plus psi is exactly equal to this sum. Alright, therefore integration phi psi dx is equal to this one. Let it be equation number 1. Alright, so phi n and psi n are simple functions such that they are monotonic increasing to the function f of x, and psi x is increasing and limit to gx. Okay, so then that means phi n plus psi n is also simple function. They are increasing also, and they are converging to the function f plus g. So from 1 we have integration phi n plus psi n dx is equal to this sum. So if you take limit both sides, you have this one, and then you put the values. Okay, so it completes the proof. Alright,